Welcome back, everybody. This is video 2 for chapter 3, and we're going to talk about kinetic energy in this example. So we have car A that has a mass of 1,000 kilograms, moving at 60 kilometers per hour. Car B, on the other hand, has a mass of 2,000 kilograms and is moving at 30 kilograms per hour. So what you'll notice is that the mass of the car doubles, but the speed halves. And so the question at the end of this chapter is the kinetic energy of car A compared to car B is what? Well, you could do this conceptually, but I'm going to work them both out, and we're going to start out with the kinetic energy of car A and plug in the numbers. 1/2 times the mass of car A, which is 1,000 kilograms, times the velocity of 60 kilometers per hour, and we can leave it in kilometers per hour, that's fine, we don't need to change units to meters per second. And we can't forget to square this, because our formula for the energy of motion, kinetic energy, is 1/2 mass times velocity squared. Okay, so our kinetic energy for car A is 1,800,000 joules. So let's do B now. The mass here has doubled, but the velocity is cut in half, and that's going to have more of an effect because velocity is squared. Okay, so when we calculate that, we get 900,000 joules. So by doubling the mass from A to B and having the velocity from A to B, the kinetic energy of car A is 2 times greater than B. All right. In this problem, we are going to talk about rest energy and mass, and this has to do with Albert Einstein's equation, energy is mass times the speed of light squared. Okay, so remember, energy and mass are so closely related that one can be converted into the other, and that's exactly what we can do with this equation. So the problem reads, an object has a rest energy of 1 joule when its mass is what? Okay, so what they're asking us to do here is solve for mass. My pen doesn't seem to be working. So rearrange the equation. Hopefully I have my pen working correctly here. So I've rearranged the equation so that mass is energy divided by the speed of light squared. They tell us that the energy is 1 joule. The speed of light is 3 times 10 to the 8th meters per second. And the one thing we cannot forget to do is to square that. So you can see that there is a lot of energy in objects which don't have very much mass at all, because we are multiplying the mass of objects by the speed of light, which is a big number, and we're squaring that on top of that. So if we take 1 joule and divide it by 3 times 10 to the 8th meters per second squared, we get 1.1 times 10 to the negative 17. And that would be kilograms for our units, since we're dealing with mass. Okay, so 1.1 times 10 to the negative 17. This, of course, is kilograms, not joules. Very, very little mass, and yet it's equivalent to a lot of energy. That's Einstein's E equal mc squared. Let's do one more problem of the conversion of mass to energy. Here they say the lightest particle in an atom is an electron whose mass is 9.1 times 10 to the negative 31 kilogram. Very small mass. What is the energy equivalent of this mass? So whenever you read these problems that want to know the energy equivalent to a mass, you're going to be using E equals mc squared. So here it's just plug away. 9.1 times 10 to the negative 31 kilograms times the speed of light squared, which is 3 times 10 to the 8 meters per second squared, and we come up with 8.2 times 10 to the negative 14 joules. Okay? So the book doesn't give you this answer as a choice. They give you an answer of, they round it because they say approximately, so the answer in the book is 10 to the negative 13. But I'm happier with just putting this answer like this at 8.2 times 10 to the negative 14 joules. And those are all the problems I'm going to do for chapter 3. So I hope this was useful for you as a student.